This is the recorded version of a talk presented at VLDB 2015. My name is Wolfgang Gatterbauer and this is joint work with Stefan Günnemann, Danai Kutra and Christos Valoutsos. Our main contribution in this work is a mathematical formulation of belief propagation that is guaranteed to always converge even on graphs with loops. And our motivation comes from the problem of labeling or classifying nodes in a network. In networks, we can often infer the most likely labels or classes of nodes based on the labels of the neighbors and known patterns of preferred interactions between nodes. An often observed pattern is that nodes like to connect with nodes of the same class, also called homophily. In this case, for this scenario here, we're trying to predict the most likely political leaning of the node with the question mark and observe that it's 4 times more likely to be connected with or friends with blue nodes than with orange nodes. And based on this, predict that it's most likely also blue. So this pattern of homophily or birds of a feather flock together, also sometimes called guilt by association, is at the core of many widely used methods in computer science. For example, even when recommending movies to users, recommender systems very often, algorithms in this area, create a bipartite graph of users and movies, and then for any target user try to find closely connected other users and whatever movies they have watched and liked in the past. Now sometimes we observe the reverse. The reverse is where opposites attract, also sometimes called heterophily or disassociative networks. In these cases, very often classes of nodes complement each other. 2 examples: when we're trying to create groups of users that work together on a project, it makes more sense to find those ones that complement each other than those that fulfill the same functions. This may create conflict. Even in nature, in protein interaction networks, we often observe that proteins like to interact with each other that fulfill different functions, and together they are able to perform more complicated, biologically meaningful functions. And if one of the proteins goes away, it may be able to be replaced by another protein of the same function. Very important, for example, in drug development. Now, for any given situation, the typical class-to-class interaction, this pattern of interaction, of attraction, can be captured with what is variantly called affinity matrix, or potential, or heterophily matrix, or coupling matrix, or compatibility matrix. The idea is the following: that if you look at this, if this matrix is normalized to 1, then we can observe the estimated label distribution for any given node, for the neighbors for any given node in the network. So for example here, this matrix expresses that a blue node is 4 times more likely to be connected to another blue node than to an orange node. And this is exactly what we would observe in this network if this node indeed is a blue node. The problem we're trying to solve in this paper is now the following. We assume we are given an undirected graph with some of the nodes labeled and some other nodes unlabeled. We are trying now to predict the labels of all the unlabeled nodes based on a given heterophily matrix. Notice here that we allow in this paper that this matrix shows both patterns of homophily and of heterophily. Homophily because in this particular example, green nodes are most likely to be connected to other green nodes, versus blue nodes are most likely to be connected to orange nodes and vice versa. The only restriction we place on this matrix is that it's symmetric and double stochastic. Double stochastic means that each row and each column sums up to 1, so that such a row just shows the average label distributions of nodes of a certain type. So blue ones connected to 80% orange nodes and vice versa, and so on. Now, this problem could be modeled with the help of undirected graphical models, but the issue is that we're trying to solve that the algorithm to solve them in practice, belief propagation, comes with well-known convergence problems, and that's what we're trying to solve in this paper. We're proposing a new formulation of belief propagation that is always guaranteed to converge, and as a side product, it also comes with considerable speedups. For the remainder of the talk, we are going to shortly revisit belief propagation. before we discuss our version, linearized belief propagation, LinBP, before we show some experiments and then conclude. Belief propagation is an iterative algorithm that allows us to infer the expected label distribution at each node. And it's an exact algorithm on trees. It was originally proposed by Pearl in his foundational work on probabilistic reasoning in Bayesian networks, for which he received his Turing Award in 2011, partially also for this particular algorithm, which is actually quite deep and well justified. We don't have the time in this talk to discuss why the way it works, but only how it works. So how it works is that nodes iteratively send messages to the neighbors. Here, for example, ST source to target, but at the same time, T also sends another message to S. Now, these messages that S sends to T contain all the information that it received in a previous step from its neighbors, except from the neighbor to which it sends this message. This is justified because the message contains all the information from the subtree rooted at the node S. Imagine all the information that this particular node can ever send to T, it needs to pass through S. This is because it's a tree, and there's no loop, and there's no other way that any node can send a message to T. There's only one particular path between every node. Now, another way to think about this is that S, before it sends a message to T, it aggregates all the information from its neighbors, but then it has to compensate, something that we refer to as echo cancellation. It needs to compensate for the message that S has received previously from T. So another example, think about the forest. Imagine that you are listening to the forest, for this example, but this is, I think, very intuitive. And if you have a machine that, let's say, like your microphone, makes a noise itself, then you're also picking up with your microphone these noise that you've produced yourself, the echo from yourself. And the idea of the algorithm and the idea of this echo cancellation is to cancel this echo and to only capture the information that really comes from this subtree and not from yourself from a previous step. Now, this algorithm continues iteratively until the message don't change anymore. They converge, and the result is then a label distribution at each node. Here, for example, at node T, assume we have this label distribution, then we can say, well, the most likely label is the second label. It has the biggest value, and therefore our prediction is that the label of this node is the second class. Now, on graphs with loops, this algorithm is not justified anymore. It's not correct from a probabilistic point of view. There's no guarantee of correctness when it converges, but even worse, this algorithm may often not converge if graphs have loops. We have an intuitive example in the backup of these slides. And it is still widely used in practice because when it converges, it gives very often observed good approximations, and there are not many other alternatives to this particular algorithm. So it's used in practice, it's not clear when it converges, and it needs a lot of fine-tuning of parameters to make it converge. So let's look at the equations of belief propagation in some more detail. So the messages that the nodes send to each other actually turn out to be vectors of messages. For example, if T has two different possible classes, then S sends a message that consists of two different messages, a vector of two messages. If one intuitively is bigger than the second message, then S thinks that T is more likely to be the first instead of the second class. Now, the equations look in more detail as follows.
Oh, that looks complicated.
So that looks complicated, but there's a well justified reason for why the equations look this way, and we refer the reader to go back to Pearl and Weiss' very nice work in neural computation that derives these equations in more detail. For us, we just look at how do these equations look like. So for each node, the explicit belief in a certain class is multiplied with all the incoming messages for this particular class, except for the one to which we send the message. It is then modulated by the heterophily matrix and summed up over all the classes before it's sent to the neighbor. At the end, after these messages converge, then at each node the explicit beliefs in a certain class are multiplied with all the messages, the incoming messages. And then, this is very important, these messages have to be normalized to sum up to 1, to represent the real probability distribution. This, in turns out, this normalization that takes place at each of the iterations is one of the reasons why it's very hard to analyze the convergence properties of belief propagation. And it turns out, once we solve this, which we're going to do in a couple of slides, then the convergence can be analyzed far more easily. So here are the same equations as before, with a slight difference. We now represent all the messages in terms of vectors. This allows to simplify our expressions in a couple of slides. The only thing what we need to do and to note to before is this particular symbol. This particular symbol represents the component-wise multiplication of vectors. So if you have, for example, two different vectors, we multiply the first component, 0, 1, 0, and the second one separately to get a new vector. Otherwise, it's exactly the same equations as before. So what now happens, just to illustrate this normalization step, is if the vector in this parenthesis is, for example, 0.4, and we have a heterophily matrix, then this modulates this vector, it gives this vector, and this vector now needs to be normalized. And this normalization happens at each iteration intuitively, and the factor by which we have to divide this changes. That's the difficulty. Here, for example, this sums up to 4, we divide by 4, and we get this value. Now, these equations often do not converge, and to make them converge, it requires a lot of fine-tuning experience with the workings of belief propagation, and that's one of the issues we try to solve. In order to solve the convergence problems. So our transformation of the update equations rely on two key ideas, centering and linearizing. With centering, we refer to the idea of centering each of the original values in the update equations around some well-chosen uninformative centering points, and then to focus only on the residuals. This means the difference from the centering points. Now notice two things. One thing is we express residuals with this hat. Second thing is, notice that the residuals still express the relative importance of labels to each other. So here, for example, the first label prefers the second one, and the same is also still captured in our residuals. Now what does this buy us? Well, this buys us that now we can focus our attention on these residuals and consider what happens if these residuals become very small. So this means if the relative importance is small and goes more and more to centering point. By doing this, we can now linearize the equations by approximating these formulas with the help of Taylor expansions, Maclaurin series. This transformation, turns out, now considerably simplifies these equations and transforms and helps us to transform multiplication into addition. So what have these transformations brought us? Well, they have brought us two things. The first thing is we have been able to replace multiplication of the messages with addition of the messages. So we have now a linear form of the equation. Second, what we show in the paper is once we start with centered messages, then these update equations, the updated residuals, they always remain centered from there on. The consequence is that we do not need any normalization step anymore, as was previously necessary in the original belief propagation update equations. And this buys a lot. This allows us to further simplify these equations and put them into a linear algebra framework. After a number of transformations, we arrive at this linear algebra formulation. So what we have here is we have now matrices that represent our final and our original beliefs. A matrix here is an n times k matrix. So for every individual node, we have here a vector, a row vector of the final belief distribution. We have here explicit beliefs for those nodes which are classified a priori. We have a weighted adjacency matrix. We have our affinity or heterophily matrix, and this particular expression here represents the echo cancellation term. Now, given we have here a linear algebra formulation, we can also ask ourselves, what is the closed form solution? This means if these equations converge, what do they converge to? And this can be expressed by the following expression, closed form solution. Vectorization here refers to the vectorization of a matrix. This means we take each of the column vectors here and stack them one above each other to get one simple vector. This is the Kronecker product. Now, this exists and only exists if the spectral radius of this particular expression is smaller than 1. Because only then can we invert this matrix. So therefore, we also have a very clear convergence criterion. When do the original updated equations converge? Well, if and only if the spectral radius of this particular matrix is smaller than 1. Now, what do we do if this is not the case? What we propose in this paper is that we just scale. We scale the residual of the heterophily matrix to such an extent that this is smaller than 1. And then we are always guaranteed convergence. Now, a couple of experiments before we conclude. Our experiments focus on two questions: how well does our approach work and how fast is it? In one line of our experiments, we used synthetic Kronecker graphs of varying sizes. We labeled 5% of the nodes, and then we used belief propagation BP to label the remaining nodes. We used this labeling as ground truth. Then we ran our approach, linearized belief propagation LinBP, and compared the classification of our approach against that of BP as ground truth. We repeat these exercises for varying sizes of the graph and for different values of epsilon. Epsilon is the scaling factor of the heterophily matrix. Now, we need to use this because if we keep epsilon as 1, this means no scaling, then neither of these approaches, BP or LinBP, converges. Now, the approach of LinBP is that we know exactly for what choices of epsilon LinBP converges, in contrast to BP, where we don't know this. We have to try it out and then see that it converges. Now, the result is that for a broad range of epsilon, LinBP gives the same classification as BP. And only when the epsilons become too small, so that we run into numerical floating point errors, then we get some difference between those two. Now, why is this so? Well, what we did is we showed that our approach, LinBP, approximates BP under the assumption that these residuals of the heterophily matrix become smaller and smaller. Now, to make BP converge, one needs to have non-very strong residuals in the first place. And for these cases, well, our approach very well approximates also the labeling of BP. So it means if BP works, then ours actually comes close to the way it works. Our classification is very similar. Now, what about scalability? So our approach is by orders of magnitude faster. LinBP is faster than BP. These experiments both implemented in Java. We see that LinBP scales linearly with the number of edges in contrast to BP. Now, we were made aware of the fact that BP can actually be, one can speed it up by using belief propagation with division. We also implemented this afterwards, and we still saw 1 to 2 orders of magnitude improvements between LinBP and an optimized BP implementation. Now, why is our approach so much faster? Well, because we put everything into linear algebra, and that we can leverage highly optimized existing linear algebra packages, and they're just really, really fast. What else will you find in the paper and the online technical reports? So for once, you find the full derivation of our theoretical results we have shown in this talk. Second, we give a SQL implementation of linearized belief propagation, SQL with recursion and standard aggregates. Third, we ask ourselves what happens if these epsilon values, the scaling factors, become smaller. It turns out then both belief propagation and linearized belief propagation converge towards a new semantics which we called single pass belief propagation. Single pass because every message only needs to be transmitted over every edge maximally once and sometimes not at all. And the semantics can be explained as a myopic version where the final label of every node in the network depends only on the closest label nodes. The nice thing about this is that this allows very fast incremental updates. And we also show detailed experiments with both synthetic and DBLP data sets. Takeaways from this talk: well, our goal was to propagate multi-class heterophily from labeled nodes. The problem is that normally using belief propagation leads to well-known convergence issues. Our solution is we center and we linearize belief propagation. This guarantees convergence and gives us also considerable speed up. Our equations can be put into a matrix algebra framework. They look like this in the final version. We can exactly give conditions when those equations converge. We also give closed form solutions. We also can implement in a SQL with recursion, with standard aggregates, and we also give an even faster semantics, which we call single pass belief propagation, which allows fast incremental updates. You find the code for both linearized belief propagation and single pass belief propagation in SQL on GitHub. And if you have any questions or concerns, please do not hesitate to contact us. Thank you.